Okay, here we have a system of equations, and they both, are very close to being solved for one variable, either x or y. I would go ahead and probably use substitution, except for let's see one thing here. So like equation 1, I'll refer to this one as equation 1. When I divide everything by 2 to isolate y, we could isolate x as well. We could just add 1 actually. But I'm going to show again 3 different methods here. We could graph it. We could graph to solve. We could use substitution to solve. Or we could use the elimination or addition method to solve. Okay, each of these have benefits. Each of them has pros. Each has cons as well. So because I'm going to graph it as well, let's go in and solve for y. So when we divide by 2, equation 1 becomes y equals, rather than writing x over 2, I'm going to write 1/2 x, right? We could multiply by 1/2 or divide by 2, essentially the same thing. And now I'm in slope-intercept form to quickly get the graph, right? Y equals mx plus b. Looking at equation 2, again, if we solve for y, okay, equation 2, I'm going to solve for y right below it. First, I'd subtract 3, and then divide everything by 6, which results in 3 over 6, which is 1/2, minus a 3 over 6, which is, again, 1/2. Well, what happens here, right? Looking at it from the start, I couldn't tell you these were actually the same equation, just written differently. But once I solve for y in each of these, I notice like they are identical. So what does that mean? Well, let's first look at the graph. So 1/2 x minus 1/2. Let's go ahead and we have room here. Let's go ahead and make every tick a 1/2. So this would be 1, 2, and so forth. Okay. So in this graph we have a y-intercept of -1/2 and a slope of up 1 over 2, right? A slope of 1/2. So up 1 over 2. So I'm really kind of going up 2 over 4 because remember I'm counting the scale here is by 1/2. Okay, likewise I could go down 1, back 2, and be here. So there's our graph. But because equation 1 and 2 are the same, right, same exact graph, every point of intersection is a solution. So this systems of equations here actually has infinitely many solutions. Okay, every single point on this line here is a solution. So it's not to say, like, a common mistake is say -infinity, infinity, or all real numbers. It's not really that, right? It's anything that lies on that line would be a solution. And how we write that, knowing this, to me that is enough. But how we would write that as a coordinate is you give me an x, and I tell you that if you multiply the x by 1/2 and subtract 1/2, right, exactly what y is, that would be a solution. We could have also done this solving for x, right? Like in the equation 1, I'd said it would really be easy to solve for x by adding 1. We could have a solution like that as well. Whatever you get, you would say, you tell me y, and in this case it's easy, right? we would do x would be 2y plus 1, because you just look at that equation 1, right? If I had solved for x, I'd have 2y plus 1 equals x. So this is x. You give me a y, and I could tell you what that is. So one more thing to note is when this is true, we say that this system is consistent. Why is it consistent? Because it does in fact have an answer, right? There is a solution. But the solution is dependent. Okay, it depends, right? The solution depends on, you tell me an x, and the solution of y depends on x. So we say consistent and dependent for this case. All right, the other two methods will actually go pretty quick, because we're going to substitute this value in for y, right, into here, because we took equation 1 and we solved for y, and we're going to plug that into equation 2, which is 3x equals 6 multiplied by y. So multiplied by that, right, the 1/2 x minus 1/2 plus 3. Okay, now let's distribute. That'd be 3x minus 3 plus 3 equals 3x. If we solve for x, I would subtract the 3x on both sides. So I'd have 0 on the left, and then on the right, I have negative 3 plus 3 is 0 as well. Anytime you end with this true statement, I never had to graph it, right? I never had to solve for both. I didn't have to identify that they are in fact the same. If I just try to use substitution, all the variables eliminated, and I end with something true like this is a true statement, then there are infinitely many solutions. I know that that is the case. Okay, the similar thing will happen with the elimination method. Let's go ahead and set it up like we would. So usually with elimination, we want the x and the y on the left, and then some number on the right. We want in that form, standard form. So in equation 1, I'd subtract x, right? I would have negative x plus 2y equals negative 1. For equation 2, I would subtract that 6y, so I'd have 3x subtract 6y equals 3. Now we have to think, how can we get one of the variables to cancel if we were to combine them? Okay, often this is called the linear combination because I'm combining these two. So probably the easiest way is look at these x's, right? If I have a negative x and a 3x, I know that I would need to multiply this top equation, let me pick an oddball color here, by 3. If I multiplied all of this stuff by 3, I would have negative 3x minus 6y plus 6y, I'm sorry. I'm multiplying by 3. I knew something looked wrong. So negative 3x plus 6y, negative 3. Okay. So now I'm adding this new equation 1 with this equation 2. Right? I'm adding these two here. Well, you could see that everything would cancel. 3x minus 3x, 0. Negative 6y plus 6y, 0. 3 minus 3, 0. 0 equals 0. It's a true statement, just like the other one. Infinitely many solutions when that occurs.